For more than 3 decades, the Linux kernel has been written almost entirely in one programming language. C, from the earliest versions created by Linus Torvalds in the early 1990s to the powerful kernels that now run servers, smartphones, supercomputers, and even spacecraft. C has been the backbone of Linux. It is fast, close to the hardware, and flexible enough to build complex systems like operating system kernels, but it also comes with a well-known downside. C gives developers tremendous power, yet that power comes with responsibility, and mistakes in memory management can lead to serious security vulnerabilities. Buffer overflows, use-after-free bugs, null-pointer dereferences, and memory corruption issues have plagued software written in C for decades. Over the years, countless security patches have been issued to fix such problems in the Linux kernel and other major systems. Now, something historic has happened. Linux has officially made Rust a permanent part of kernel development, marking one of the most significant shifts in the history of the project. To understand why this moment matters so much, we need to look at the broader context of software security and modern programming languages. Over the past decade, researchers and security teams have repeatedly found that a large portion of software vulnerabilities come from memory safety issues. Reports from organizations like Microsoft, Google, and the US Cybersecurity and Infrastructure Security Agency have consistently shown that around 60 to 70% of serious vulnerabilities in major codebases are related to memory management problems. These are exactly the types of bugs that languages like Rust were designed to prevent. Rust is a systems programming language that offers performance comparable to C and C++, but with a unique approach to memory safety. Instead of relying on garbage collection, like many modern languages, Rust uses a compile-time ownership model that ensures memory safety without runtime overhead. When Rust code is compiled, the compiler checks strict rules about how memory is accessed and shared. If a program violates those rules, the code simply will not compile. This means many common classes of bugs never even make it into the final executable. The result is software that is both fast and significantly safer. Because of these advantages, Rust has gained massive popularity among developers. In fact, for several consecutive years, it has been voted the most loved programming language in developer surveys. Companies like Mozilla, Microsoft, Amazon, and Google have all invested heavily in Rust projects. But bringing Rust into the Linux kernel was not a simple decision, and the journey to this moment took years of debate, experimentation, and collaboration within the open source community. The first serious discussions about Rust in the Linux kernel began gaining traction around 2020. A group of developers started working on a project called Rust for Linux, which aimed to make it possible to write certain kernel components in Rust while still integrating with a massive existing C codebase. This was not about rewriting the kernel from scratch. That would be nearly impossible given that the Linux kernel contains tens of millions of lines of code developed over decades. Instead, the goal was to allow new components, particularly device drivers, to be written in Rust, while the core kernel remained largely in C. Device drivers are an especially important area because they are often written by hardware vendors and can introduce bugs that compromise the stability and security of the entire system. Over time, the Rust for Linux project gained support from prominent figures in the open source world. Major technology companies also showed interest because they rely heavily on Linux for their infrastructure. Engineers from companies like Google and Meta contributed to the effort, recognizing that safer kernel code could significantly reduce the risk of security flaws. After multiple rounds of development and review, the Linux kernel maintainers began gradually integrating infrastructure that allowed Rust code to be compiled and linked with the kernel. In 2022, the Linux 6.1 release officially included initial Rust support. This was a groundbreaking step, but at that stage, Rust was still considered Even after that milestone, many questions remained. Some kernel developers were enthusiastic about Rust, while others were skeptical. The Linux community has always been cautious about introducing major changes that could complicate development or reduce performance. One concern was whether Rust would increase the complexity of the build system. Another concern was whether kernel developers, many of whom had spent decades writing C code, would be willing to learn a new language with unfamiliar concepts like ownership, borrowing, and lifetimes. There were also questions about long-term maintenance. If Rust code entered the kernel, who would maintain it, review it, and ensure that it stayed compatible with the rest of the system? Despite these challenges, progress continued. The Rust infrastructure in the kernel matured, more tools were developed, and early drivers written in Rust began to appear. Developers demonstrated that Rust could integrate cleanly with existing kernel APIs through carefully designed abstractions. These abstractions allowed Rust code to interact with low-level kernel structures while still preserving safety guarantees. Over time, it became clear that Rust was not just a theoretical experiment, but a practical addition to the kernel ecosystem. Slowly, the conversation shifted from whether Rust should be allowed in the kernel to how it should be used effectively. Now the historic shift has arrived. Rust is no longer considered an experimental addition. Instead, it has been accepted as a permanent part of Linux kernel development. This does not mean the kernel will suddenly become mostly Rust, nor does it mean C is going away anytime soon. C will remain the dominant language of the kernel for the foreseeable future. However, the door is now officially open for Rust to play a growing role, especially in areas where memory safety can provide significant benefits. The decision marks the first time in Linux history that another language has been formally embraced alongside C for kernel development. This moment is historic, not only because of what it changes technically, but also because of what it represents philosophically. The Linux kernel has always been one of the most conservative major software projects when it comes to technology choices. Stability, reliability, and long-term maintainability are top priorities. For the maintainers to approve Rust as a permanent part of the kernel means they see clear long-term value in the language. It signals a recognition that the software landscape has evolved and that new tools can help address problems that have persisted for decades. One of the biggest benefits of Rust in the kernel will likely be improved security. Many vulnerabilities in operating systems stem from memory safety issues. By allowing drivers and other components to be written in Rust, developers can eliminate entire categories of bugs before the code ever runs. This could significantly reduce the number of critical security flaws discovered in the kernel over time. For companies and organizations that depend on Linux to run critical infrastructure, this improvement in security could have enormous implications. Another important advantage is reliability. Kernel bugs can cause system crashes, data corruption, and unpredictable behavior. Rust's strict compile-time checks help ensure that code behaves correctly under complex conditions, such as concurrent access to shared data. Concurrency bugs are notoriously difficult to debug in large systems, but Rust's design makes many of them much easier to prevent. As more kernel components adopt Rust, the overall stability of Linux systems could improve. There is also a long-term impact on developer productivity. While Rust has a steep learning curve initially, many developers report that once they understand its concepts, they write fewer bugs and spend less time debugging. The compiler acts almost like a powerful assistant, catching mistakes early in the development process. In a project as massive and complex as the Linux kernel, this could save countless hours of work and reduce the risk of subtle errors slipping through code reviews. Of course, the transition will not happen overnight. The Linux kernel is one of the largest collaborative software projects in history, with thousands of contributors around the world. Integrating a new language into such a project requires careful planning, documentation, tooling, and community support. Developers will need guidelines on when Rust should be used, how Rust modules should interact with C code, and how to maintain consistency across the codebase. Over time, best practices will emerge as more developers experiment with Rust-based kernel components. Another factor to consider is the broader ecosystem around Linux. Device manufacturers, operating system distributions, and open-source contributors all interact with the kernel in different ways. As Rust becomes a permanent part of kernel development, tools and frameworks will likely evolve to support it. Build systems, debugging tools, and documentation resources will expand to include Rust-based kernel modules. Universities and training programs may also begin teaching Rust as part of systems programming courses, preparing the next generation of developers to work on projects like Linux. This change also reflects a larger trend across the software industry. For decades, C and C++ dominated systems programming, but as security threats have grown more sophisticated, many organizations have begun searching for safer alternatives. Rust has emerged as one of the most promising solutions because it combines performance with strong safety guarantees. The fact that the Linux kernel is now embracing Rust reinforces the language's credibility and could accelerate its adoption across many other projects. Major tech companies are already moving in this direction. Microsoft has experimented with Rust components in Windows and Azure. Google has integrated Rust into parts of Android. Amazon has used Rust in several high-performance cloud services. With Linux now officially supporting Rust in the kernel, we may see even more companies invest in Rust-based infrastructure. Over time, this could reshape the landscape of systems programming. For the open source community, the decision also highlights the collaborative nature of Linux development. The integration of Rust did not come from a single company or organization. It was the result of contributions from developers around the world who believed in the potential of safer systems programming. Through discussions, patches, reviews, and experiments, they gradually built the infrastructure needed to make Rust viable in the kernel. The final decision to make Rust permanent reflects the consensus that emerged from this collaborative process. There are still challenges ahead. Maintaining compatibility between Rust and the existing C code base will require ongoing effort. Kernel developers will need to ensure that Rust abstractions remain efficient and do not introduce unnecessary overhead. Documentation and training resources will need to expand so that contributors can learn how to write kernel code in Rust effectively. But these challenges are manageable, and the benefits appear to outweigh the risks. Looking forward, the presence of Rust in the Linux kernel could open the door to entirely new possibilities. Developers might create safer subsystems, improved driver frameworks, or innovative kernel modules that leverage Rust's strengths. Over time, we may even see hybrid components where Rust handles high-level logic, while C manages extremely low-level hardware interactions. This combination could offer the best of both worlds, the maturity and performance of C with the safety and reliability of Rust. Perhaps the most remarkable aspect of this historic shift is that it demonstrates the ability of open-source projects to evolve. The Linux kernel has been around for more than 30 years, yet it continues to adapt to new technologies and challenges. By embracing Rust, the project shows that even the most established systems can change when the benefits are clear. In the end, the decision to make Rust a permanent part of Linux kernel development represents more than just a technical update. It is a signal that the future of systems programming is changing. The era when C was the only viable language for operating system kernels may be coming to an end. Instead, we are entering a new phase where safety, performance, and reliability can coexist through modern language design. For developers, security researchers, and technology enthusiasts, this moment will likely be remembered as a turning point. Decades from now, when people look back at the evolution of the Linux kernel, they may see this decision as the moment when a new generation of systems programming truly began. Rust did not just join the Linux kernel, it became part of its future, permanently shaping how the world's most important open-source operating system will be built for years to come.